Chapter 4.2, exponential and logistic modeling. So if you remember 4.1 from whenever that was last year, we talked about exponential growth and logistic growth. Logistic growth is modified exponential growth. And remember, the number one characteristic for exponential growth is, we've already talked about it, the more you have, the more you get. The more you get. Okay, so anything that increases by a constant factor, like doubles or triples or halves every so often, or increases by a certain percentage. Those are all multiplicative. That's going to end up being exponential growth or exponential decay. Now, in this section, we are going to look at the types of situations where we might experience such a thing. And the first one is going to be compound interest. As Peyton already asked, compound interest. Have you heard of compound interest? You got your interest, and then you got your compound interest, right? Like, I'm interested in surfboards, but compound interest is I'm interested in surfboards and in surfers, right? That'd be compounded. That's not what we're talking about. Compound interest means, I don't know, I'm shooting from the hip here, guys. I didn't spend 9 weeks trying to come up with a surfboard analogy for compound interest. That just came out. So you got to think on your feet when you're a math teacher. Compound interest means the more that you earn, the more you get, because you end up earning interest on your interest. The interest that you earned previously gets added to your lump sum, on which you can then earn interest on what you've already gained. That's why we call it compounding. So the more that you have, the more that you earn. And here's a quick little example. We like to talk about food. Oh, don't we? Happy Thanksgiving hangover. And we like to talk about money, which now it's Christmas shopping season. So at least today is Cyber Monday, and you can save some money by finding excellent deals on electronics, supposedly. Let's start with the value of $100. So everybody, I'm giving you a free $100, right? Imaginary $100. Here you go, everybody. Take one per person. There's not enough to go around. Okay, good. We got that. Now, assuming that amount that I just gave you increases by 30% every year. That's pretty ambitious. There's no bank that's going to give you 30% interest. Maybe 5%, maybe 6%. But 30%, that's pretty good. But for the sake of this model, let's assume that your $100 will increase by 30% every year. Write a model to predict the amount A after a generic T number of years. We want to come up with an exponential model that allows us to find how much we have at any given time T in years. Okay, 10 years from now, 100 years from now, 3 years from now, whatever. All right, so the first thing that we're going to do is we're going to start looking at a pattern. We're going to try and recognize a pattern, because if mathematicians are anything, they are pattern recognizers. All right, so let's come over here and we'll let n equal how many times we're compounding it. N is the number of compoundings cycles. Okay, so when n is equal to 0, that's where we're starting, right? We're starting at n equals 0. How much money do we have? We have $100. Yay! I'm going to get rid of the dollar sign because it gets too confusing. But we have $100. So the amount A equals $100. Everyone agree? Okay, good. If you didn't agree, I would have to ask you what you did over Thanksgiving. Like, did you get kicked in the head by a mule? Or did you fall down a well in Prague, right, and hit your head on the way down? All right, after 1 year, how much do we have? Well, we still have our $100 from the year before. Yes, yes? Plus, we have an additional 30%. Now, how do we show that we're finding 30% of 100? I don't ask you what 30% of 100 is. How do we find 30% of 100? In general, or a percentage of a certain number is what operation? Multiplication. So I'm going to take my $100 and I'm going to multiply it by 30%, which has a decimal as what? 0.3. Okay. Now, of course, I chose 100, so 100 is an easy number to work with. What's 0.3 times 100? 30. So I gain another $30, so I have $130, right? Now, I'm looking for a pattern, so I'm not going to write $130. I'm not interested in knowing exactly how much I have. I want to pick up on a pattern that's a function of the number of times I've compounded it. So here's what I'm going to do. I'm going to answer the door, and maybe that's Helena. I should probably switch the doorbell. No, oh no, it's Carly. Merry Christmas, Carly, and a Happy New Year. Thank you. Ryan Simmons, you're checking out at 9:30. You just got here, bro. Was it something I said? Okay. Do you notice in the two terms I have a common factor of 100? You'll see that? What can we do with common factors when we have them in multiple terms? We can F it out, right? When in doubt, F it out. 100 times. What do we get when we factor out 100 from 100? What's left? Well, no, in the first term. We're left with a 1, aren't we? Remembering factoring out is the same as dividing out. So we're left with 1 plus 0.3. Now I'm working left to right here on purpose because I want to see the patterns as I work down. Well, what's 1 plus 0.3? 1.3, so that's times 1.3. So I have 100 times 1.3. That makes sense, right? What's 100 times 1.3? $130, right? You just move the decimal 2 places to the right. So this is the same thing that you do when you calculate your tax on like a food bill. I don't know if you've ever done that, but you have your subtotal, and then you have the tax. And the tax is usually like 8 something percent, and you can see the tax amount. It's 0.8 times your subtotal, and then it's added back to your subtotal for your final amount. And then, of course, you have to calculate how much you're going to tip on that, 15, 20%, whatever. But this is how your bill is calculated when you have tax. You have your subtotal, and then you have your tax. You add them together, and you get your actual amount. Well, the $30 here would be like the tax, and the 100 would be like the subtotal. So the 1 in the 1.3 stands for 100% of the previous amount. And the 0.3 stands for the additional 30%. That's an important thing to recognize. The 1 and the 1.3 stands for 100% of the previous amount. You get everything that you had before, plus an additional 30%. That's because 1.3 as a percentage is 130%. You get 100%, everything you had before, plus an additional 30%. Okay, now for what it's worth, if you want, you could say that's $130. I'm not really interested in that number. I'm interested in this right here. Okay, that's after 1 year. Let's look at 2 years. The amount at 2 years is going to be my previous amount, which is now 130. Yes, yes? Plus an additional 30% of 130, which is 130 times 0.3. Yes, yes? I don't want to use 130 there. 130 is going to mask my pattern. I don't want to use 130 there because it's going to mask my pattern. So here's what I'm going to do. Instead of using 130, which y'all, that makes sense what I just did, right? I'm going to use that version of it. So we have everything that we had before, 100 times 1.3, plus another 30% of that. Well, that's going to be 100 times 1.3 times 0.3. And that, if I now factor out the 100 times 1.3, I'm left with 1 plus 0.3. Everyone with me so far? Just what we did above, except instead of using 130, I'm using 100 times 1.3. Now, just like before, I have 100 times 1.3, that's my previous amount, times, what's 1 plus 0.3? Another 1.3. And alas, since these are the same base, what can I do with their exponents? That's to the first power, that's to the first power. When the bases are the same, what do? We don't eve them, we what? We add them. That's what I was looking for. Adam and Eve, right? We add them. We don't eve them, we add them. Yeah. That's 2. Okay. We wouldn't keep squaring it, but we would keep adding an exponent. That's the pattern we're trying to go for here. Now, I don't know what 130 times 1.3 is. I'm not interested in the actual amount. I'm interested in capturing the pattern. So here's what I've already noticed so far, that my highlighter is just a smidgen too large. There we go. I noticed that when n is 1, this came out to be 100 times 1.3 to the 1th power. Now, when n is 2, this comes out to be 1.3 to the 2th power. Do you see the pattern that's emerging? Let's try one more before we go through the general pattern. Let's try one more. When I compound it 3 times, or after 3 years, we're going to have the amount is equal to the previous amount. The previous amount is now 100 times 1.3 squared, whatever that is. Would you all agree? That's the previous amount. We get all of that, plus an additional 30% of that, bless you. An additional 30% of that is 100 times 1.3 squared, that's the previous amount, times another 30%. Well, now I can factor out my 100 times 1.3 squared, and I'm left with 1 plus 0.3. That turns into 100 times 1.3 squared times 1 plus 0.3 is another 1.3. And now, since those bases are the same, what do I do with them? I add them together, and I get 1.3 to the 3rd power. So look at this. When n equals 3, that is when I've compounded it 3 times, I get to the 3rd power. Now here's what else I can do. Instead of letting it equal n, I can also let it equal t, which maybe would have been appropriate from the very beginning, where t is the number of years, right? It's the same thing. After 1 year, I've compounded it once. After 2 years, I've compounded it twice. After 3 years, I've compounded it 3 times. Do you see where that 3, that is my counter over here, where it is appearing in my pattern on the final line here? It's appearing as the exponent. So look what we could do here. If I keep this pattern going, eventually I can get down to t equals t years. Okay, or I could say where n equals t. Let's do n, where the number of times I'm compounding it in general is t. The amount now, as a function of time, should end up being 100 times 1.3 to the tth power. That's a direct consequence of this pattern over here on the right-hand side. In other words, my independent variable, that was the counter of the number of years I've compounded it, t years or n compounding cycles, ended up being the exponent. And what stayed the same all the way through it? The 100 stayed the same, and the 1.3 stayed the same all the way down. The only thing that changed was the exponent. That's pretty fantastic. We have just come up with the model that allows us now, not by recursive operations. What we're doing up here, this is called recursive operations. Let's talk about what that means. Recursive operations. A recursive operations, it relies on the previous calculation. Right? In order to figure out what I have after 4 years, I have to take what I had at year 3 and add another 30%, right? If I want to know how much I have after 30 years, I have to know what I had at 29 years and add 30% to that. That's called a recursive operation. That's pretty good if you can get it down to a recursive pattern. But guess what we have now? We have the Holy Grail. This is a formula. That's a function of t. So if I wanted to know how much I had after 30 years, I wouldn't have to figure out what I had the first 29 years just to add 30% to that. I could just plug in a 30 directly into the formula and save all that work of having to build up the previous years. If I wanted to know what I had after 5 years, I just plug in a 5. If I want to know what I had after 1,000 years, if I lived that long, right? I can just plug in 1,000 for t. All right, now, this is the Holy Grail. This is what we're after again. I put it in a box. Let's analyze what these numbers are, okay? What stayed the same? The 100 stayed the same all the way through. What was the 100 in the original context of the problem?
The initial value.
It was the initial value. That should always be the case. You could work it with different numbers. You could start with $1,000 or $10 or $5, whatever you want. And you'll see, if you do the same thing we did above, that this will always end up being the initial amount. Okay? What else is the same? The 1.3 is also the same, isn't it? What does the 1.3 represent? It represents a 1 plus a 0.3, doesn't it? Which ends up being the same thing as 100% plus the additional 30%. That also stayed the same. So if you were getting 40% every year instead of 30%, what would the new base of the exponential function be? By the way, this is an exponential function. Would you agree? I probably should have pointed that out. We have a variable exponent t instead of x and a numeric base. And is this growth or decay? It's growth because the base is what? Greater than 1. Yeah. So if you were getting 40% every year, what would your base be? 1.4. It's 100% of what you had previously plus an additional 40%. So that would be 1.4. Those are the two things that are going to stay the same. And then your t is, of course, your variable. And then we could say a of t because it's a function of t. All right, so if we're going to generalize this, we could say a of t is going to be equal to a sub o times 1 plus little r to the tth power. A sub o is your initial amount. Initial amount. That's where the subscript 0 comes from. That means your amount at times 0, a sub o. The 1 is the 100%, and then the r is going to be your growth rate as a decimal. Your growth rate as a decimal. So see what we already did there. We went from something very, very specific to something very, very general. And now I can change things up. I could start with $500 at 2% interest. $500 at 2% interest. What would the equation be if it was $500 to start with 2% interest? It would be 500 times 1 point what? 0.02. 1.02. That would be to the tth power. That would be how much you'd have after 2 years. That's compounded interest, okay? And you have an explicit formula now for finding it. Exponential growth. Okay? That's pretty cool. Now, t is measured in years, okay? So that if you're compounding it more often than once a year, you would have to have a different formula. This assumes that we're compounding it each year. Sometimes banks compound it more than once a year. Sometimes they compound it monthly. Here's the deal, though. The more often you compound it, that is, the more often you go back in and look to see what the current amount is and then give interest added back to that, the faster it grows, okay? The more often you compound something, the faster something grows. Banks usually do it monthly. Anyone heard of a credit card? Credit card means you're borrowing money from a bank on a whim. You don't even need to get pre-approval. You can just buy anything, put it on credit, and when you get your credit card bill, the interest rates are always a lot higher than what the banks are going to give you if they're using your money. Because you're paying the bank, the interest rate is usually higher. Like at a bank, you could probably get 3 to 5 to 6% interest. That is, they'll give it to you, the money to you. If you look at credit cards, sometimes they're up to 18, 25% interest. And they don't compound it monthly. If you look at the receipt when it comes in, it says they compound it daily. Wow. So credit cards are dangerous if you don't know how to use them because you're paying very high interest rates and it's being compounded daily, which means your money that you're owing them at that higher rate is growing faster. The more often you compound something, the faster it grows. So it's funny how that works, right? When the banks are paying you, it's like, oh, we'll give you a small amount every so often. But when you owe them, it's like, you're going to give us a large percentage every day. Be careful with credit. All right. Any questions on that? Example 2. This is a good thing to talk about as we start our Christmas shopping for the year, right? Just put it on credit. If you pay your credit card bill off every month, that's good. Now the credit card is for convenience, and you can get the perks because now they're offering like cash back. You pay it off every month, you get the convenience and the perks, but you're not giving them any extra money because you're paying it off. And the banks are like, shoot, darn it. We're not earning money on you, but most people don't pay the balance off every month. And that's where banks get rich. People sometimes go into amazing debt. So be careful out there. When you pay with a credit card, it doesn't feel like you're using real money, right? It's just like this plastic thing's like a magic wand. Give me that, give me that, give me that. Example 2. Let's start with an initial value of $100. So I'm giving you another imaginary $100 again. Assuming now, oh no, that this amount decreases by 30% every year. Write and predict the model for A after T years. You want to see the pattern again? You want to do what we did to start the other one? We'll see the pattern? Let's do that. We'll let T equal 0. We'll use T instead of N this time all the way. But T is still the number of compounding cycles because we're doing it every year. So at T equals 0, we have $100. No big deal. At T equals 1 year now, we're going to take our $100, but now instead of adding 30%, we have to what? We have to subtract 30% of 100, which is 100 times 0.3. Now, of course, I'm not interested in what this actually is. What is 30% of 100 again? $30. And what's 100 minus 30? We're down to 70 after 1 year. Oh, no. I don't care that we're calling it 70. I want to look for a pattern as a function of T equals 1. So if I notice there's 100 that's common in both, I'll factor out the 100, and I'm left with 1 minus 0.3. And, of course, what's 1 minus 0.3? 0.7 to the first power. So that's another way to look at it. Instead of saying, hey, I'm losing 30% every year, that would be the glass is half empty kind of perspective, right? Oh, shucks, I'm losing 30% every year. Woe is me. The optimist, the glass is half full guy, will say, hey, well, at least we're retaining how much? We're retaining 70%. So look on the bright side. We're losing 30, but we still get to keep 70%. The formula that we're going to come up with gives us a base that tells us how much we have, not how much we've lost. It tells us what the amount is at any given moment. So it forces us to be optimistic. We're not going to focus on the fact that we've lost 30%. We're going to focus on the fact that we are keeping 70%. 7%. All right, let's do the pattern with one more year here because it's kind of fun. Kind of. All right, let's go after 2 years. I'm taking my previous amount. I should say that this is A of 0. I should squeeze this in here. This is A of 1 now. This would be A of 2. I'm taking my previous amount, which is 100 times 0.7 to the first, and I'm losing another 30% of that. So I take my amount, 100 times 0.7, and I multiply it by 0.3, and I subtract it. Well, now you can see that I have this common factor. So I'll factor out the 100 times the 0.7, and I'm left with 1 minus 0.3, which turns into 100 times 0.7, my current amount, times 1 minus 0.3, which is another 0.7. And now since those bases are the same, what do I do with the exponents? I don't eve them, I add them. Right, add them. So I get 2. So there you can see that we have t when t equals 2, it's 0.7 to the second power times 100. All right, so now if I just go all the way down to when n equals t, the number of compounding equal t, I get the amount at any given time should be, well, what is this pattern going to look like? It's going to be 100 times 0.7 to the tth power. 100 times 0.7 to the tth power. And let's dissect this again like we did previously. This 100 right here is our initial amount, right? Remember, exponential growth or decay cannot grow or decay out of nothing. There has to be some seeded starting value. And in this case, it's the 100. The 0.7 is it's the percentage. The percentage, let me write that out here. The percentage we retain as a decimal. You can do that when you're in the store. Like if the store is having a 20% off sale, let's say the original price is $100 and Black Friday it's 20% off because Black Friday deals aren't what they used to be anymore. Is that important?
Yeah.
Okay, we'll reply. Say thanks or something.
All right.
Comma, I love you too. If it's 20% off and it costs $100 to begin with, you can calculate the price you're going to have to pay by saying, okay, it's $100, but it's 20% off. So I'm saving 100% times 20%, or 100 times 20%, which is $20. I'm saving $20. So what am I going to pay? Well, if it was 100 and I'm saving 20, 100 minus 20 is 80. So it's going to cost me $80. That's how most people calculate what it's going to cost them. But the savvy person now can say, hey, if it's 20% off, I'm still paying for what percentage of it? 80. I'm still paying for 80% of it. That's how much of the value is being retained. So what's 80% times 100? 80. You do it with a single calculation instead of two calculations. You don't calculate the amount you're saving and then subtract from the original amount. You're just calculating how much you're paying. You're saving 20%, which means you're still paying 80%. So on and so forth, et cetera, et cetera. So be mindful of those Cyber Monday deals. All right, now, can we generalize this even more to any given amount? I think so. In general, A of t is going to equal to A sub O, the initial amount, times 1 minus R to the tth power. That should be the general way to write it. And A sub O is still your initial amount, or the amount at time 0. That's where the sub-zero comes from. And little r is your decay rate as a decimal. We call it the decay rate. If we're losing, we call it the decay rate, and it has a decimal.
So is that the model we will always use?
That's the model we'll always use, yeah. If it's growth, we're going to use 1 plus r. And if it's decay, we're going to use 1 minus r. All right? So let's summarize right here. Exponential growth or decay model. If an amount A is changing at a constant percentage rate R, okay, capital R is the percentage rate. Okay, capital R is the percentage rate at each time period t. Then A of t is equal to A sub O times 1. Let's put a plus or minus R to the tth power. I don't have the minus sign under the plus sign. So let's just turn 1 plus R into 1 plus or minus R. I need to change that. 1 plus or minus R to the t. Where little r is what? Little r is essentially big R, but as a decimal. So if big R is 80, because it's 80% off, that'd be great. Black Friday deal, 80% off. Then little r would be 0.8. Got it? So that's, we keep the same letter. Big R is the percentage, little r is the decimal. Okay, that's what it says right there. Where little r is big R expressed as the decimal. All right, now this is important. If A of t is called as exponential growth, then big R is called the growth rate, and 1 plus R is called the growth factor. Okay, so an example would be 80%. 80% is the growth rate. And 1.8 is the growth factor. This is vocabulary here. We have to know the difference between a rate and a factor. It's easy to remember what the factor is because it's built right into the equation, right? 1 plus r in this case is the base of the exponent. And every time you increase t by an extra value of t, 1, 2, 3, 4, you're picking up an extra factor of 1 plus r. So if you want to make a note to yourself, 1 plus r, the growth factor, is also the base. That's important. I will ask you questions on quizzes and tests. What's the growth rate? You'll say 80%. What's the growth factor? 1.8. Got it? Okay. So these two are equivalent now. If something increases by 80%, it's increasing by a factor of what? 1.8. Let's try this one. If something increases by a factor of 100%, if something increases by a factor of 100%, what would be the growth factor? 2. It doubles, right? That makes sense. If something increases by 100%, then little r is 1, and 1 plus 1 is 2. The growth factor is 2. It doubles. A lot of people don't put those two things together. If something increases by 100%, it doubles, right? It doubles. Okay. What if something increases by 200%? What's the growth factor? 3. Then something triples. If something increases by a factor of 200%, it doesn't quadruple, does it? It only triples. Oh, that's wild. That's crazy wild stuff. Go gadget math. What would the percent increase need to be if something triples or if something quadruples? If something quadruples, what would the growth rate need to be? 300%. Very good. You see the difference between them? The growth factor always has the extra 100% in there. All right. Similarly, if A of t is exponential decay, then big R is called the decay rate. So again, you could say an example might be 20%. Something decays by 20%. That's the decay rate. 1 minus R is called the decay factor, and that would equal what? It would be 1 minus 0.2 now, which is what? 0.8. That's the growth. All right, we'll see you. That's the decay factor, not the growth. That's the decay factor. But it's also going to be the base. It'll be the base in the equation. Now, these you have to be a little bit more careful of. If the decay rate is 20%, what's the decay factor? It's not 0.2, is it? That's an answer choice that I'll put. If the decay rate is 20%, is the decay factor 0.2? No, it's 0.8. Because if we're losing 20%, we're retaining what? 80%, and the base then is 0.8. Remember, the base is always how much we have left. When we talk about a decay rate and a growth rate, that's always going to be some positive number. We have to decide if we're adding it or subtracting it. And that's where the growth or decay factor comes in. We have to know whether we're adding it to 1, which is easier, or if we're subtracting it from 1. But we're always working off 100%. We're either getting extra added to the 100% or we're losing from the original 100%. All right, very, very important. If the decay rate were 75, if the decay rate were 75%, what would be the decay factor? 0.25. Very good. It's easy to tell in your head, hey, if it's 75% off, we are retaining 25% of what it was, and therefore the decay factor is 25% as a decimal, which is 0.25. You might be able to find some 0.25 decay factor cyber deals, especially if the technology is broken or returned or refurbished, right? Then you can get it. Yeah, hand me down, 75% off, like the iPhone 5. Example 3. Determine the growth or decay rates and the growth or decay factors for each of the following. Okay, first of all, this is an exponential growth or decay? It's growth. What's the base? 1.046. That's the base. What's the initial value? 6. And we know it's exponential because we have a number raised to a variable power. For applications, we're using t instead of x. That's not a big deal, right? We're using t instead of x. Is this growth or decay? It's growth. So if the base is 1.046, is that the growth factor or the growth rate?
growth factor.
The growth factor. Very good. Okay. It's easy to remember the base as the factor because think of it again, just adding another value of t, we're just adding another 1.046. We're multiplying by another 1.046. So the growth factor, which you can abbreviate GF, is 1.046. So you can put GF equals 1.046. That would be fine. The growth rate, which you can abbreviate GR, is what? 4.6, and we'd have to add a percentage to it. The growth rate is always a percentage rate. Okay? How did I get 4.6, or how did you get 4.6, Peyton? Yeah, I would convert it to a percentage first. Take your base, whatever it is, convert it to a percentage by moving the decimal 2 places to the right. So this is 104.6%. And then all you got to do is take the difference between it and 100. If it's bigger than 100, it's easy to find. If it's smaller than 100, you have to do subtraction. So convert it to 100%, or convert it to a percentage, and then find the difference from 100. So 104.6% is 4.6 bigger than 100. Okay? Excellent. You got it. Convert the GF to a percent by multiplying by 100. Instead of an asterisk, let me call that number 1. And number 2, find the difference from 100. That's how you find the growth rate from the equation. Okay? So we're going backwards here. Instead of giving the verbal model, saying it increases by 4.6% and trying to come up with the equation, we're starting with the equation, and we're trying to find the growth factor, growth rate. All right, let's look at this one. Letter B. M of t is 3 times 0.14159. Anyone see pi in there? Man, I got a lot of pie over the break. I didn't realize that pie was delicious for breakfast. Did y'all? Y'all know pie? There's no rule against eating pie, leftover pie for breakfast. There's no rule. Not at all. There's not even rules how many pieces you can eat. 5 pieces of pumpkin pie for breakfast? Yeah, and you're probably like, oh, I should have not eaten that many. But hey, no one else in the family eats leftovers, and you were raised to not throw stuff away. So you end up just getting fat and uncomfortable. But anyway, enough about me. Is this growth or decay? It's decay, because what's the base? Less than 1. It's 0.14159. So the base, it's easy to find that one first. The base ends up being the growth what? Or the decay what? The decay factor, which you can call the DF, is 0.14159. 0.14159. Okay? It's the base. So you could say DF equals 0.14159. The decay rate, which you can call DR, is going to be what? Well, if I convert 0.14159 to a percentage, I'm going to have to do 14.159. And then because it's decay, what do I do with that? Do I add it to 100 or subtract it from 100? I got to subtract it from 100. Does anyone have a calculator? 85.831? Yeah, that'll work. Thank you. Yeah, 85.831. So there it is. So your decay rate, you could say DR. You could do that off to the side on your workbench, or you can just do it on your calculator. 85.831. Just make sure you add the percentage sign afterwards. Okay? 85.831%. There you go. It's fun easy, right? Fun easy. All right, let's try this last one here. 7 times 2 to the x. Is this growth or decay? Growth. So your growth factor is what? 2. And your growth rate is what? convert it to a percentage, that's 200%, and then find the difference from it and 100. Since it's bigger than 100, we subtract 100 from it and we get what? 100%. We've already talked about this, haven't we? If something doubles, it increases by 100%. If something increases by 100%, it doubles. Okay? That's all we have time for today on today's episode of Exponential Growth and Decay Models. But hopefully now you know to be very careful with your credit cards, right? Be careful with your credit cards. All right, so we got through example 3. Any questions? Fantastic. I did a great job today.